Picture this, a solid block of titanium. In just a matter of minutes, it's completely transformed into a perfectly toleranced aerospace component. You've got metal chips flying everywhere, coolant spraying. It's this awesome, cinematic display of brute force, right? Well, actually, beneath all that apparent chaos is a world of absolute, uncompromising mathematical precision. Welcome to this explainer on the calculation and design of cutting tools. Today, we're going to bridge that gap between theoretical machining principles and physical manufacturing reality. We're diving into exactly how engineers design the very tools that literally build our modern world.
Okay, here's our game plan for today. We'll start with an introduction to tool design. Then, the fundamentals of cutting geometry. Third, we'll walk through the engineering design workflow. Fourth, designing non-standard tools. Fifth, designing standard cutting tools. And finally, designing gear cutting tools.
All right, let's jump right into Section 1, Introduction to Tool Design.
So think about this for a second. How exactly do engineers figure out the geometry of a cutting tool before the thing even exists? I mean, you can't exactly just guess and hope for the best, right? It takes a really deep synthesis of machining theory, material science, and some seriously rigorous mathematical calculations based entirely on the specific workpiece you're trying to create.
And that brings us to this incredible chain reaction in manufacturing. It's almost like a domino effect. Proper tool design directly dictates your cutting performance. That performance guarantees your dimensional accuracy and surface quality. And when you get all of those dialed in perfectly, tool life goes way up, which ultimately skyrockets your overall productivity. But flip that around. If your tool geometry is even slightly off, you're looking at excessive cutting forces, rapid wear, crazy vibrations, and, totally ruined workpieces. Basically, getting the geometric calculation right from the start is the absolute best way to prevent manufacturing disasters.
Moving on to Section 2, Fundamentals of Cutting Geometry.
Let's talk about the first really critical parameter here, the rake angle, which we denote with the Greek letter gamma. This is essentially the angle of the tool face relative to a plane perpendicular to your cutting direction. Physically, this angle decides exactly how the metal chip flows off your workpiece. So, if you're doing some heavy-duty rough machining, you're probably going to want a smaller or maybe even a negative rake angle to give the tool maximum strength. But if you're finishing a part and need a totally flawless surface, a highly positive rake angle is what you want. It shears the metal super cleanly and really drops those cutting forces.
Next up is the clearance angle, or alpha. Now this is the angle between the tool's flank and the freshly machined surface of your workpiece. Here's the deal. If you calculate this angle too small, the back of your tool is literally just going to rub against the metal. That means massive friction, a ton of heat, and a really fast tool failure. But if you calculate it correctly, you make sure that only the microscopic cutting edge is actually touching the material. This totally prevents vibration and drastically extends the life of your tool.
The big takeaway here is that these fundamental angles are absolutely not arbitrary. They are highly engineered for very specific jobs. Just think about how they compare across different tools. If we're talking about circular form turning tools, your clearance angle alpha is usually calculated right between 8 and 12 degrees. But then consider a standard twist drill. Its standard point angle is usually engineered at exactly 55 degrees so it can efficiently punch into solid material. On the flip side, a finishing reamer, which is just there to smooth out a hole you already made, often uses a 0-degree rake angle so it doesn't accidentally overcut. Literally every single angle serves a very calculated purpose.
All right, let's shift gears to Section 3, the Engineering Design Workflow. This is the classic 10-step workflow that takes a concept all the way from a blueprint into reality. First, it always starts with the workpiece. We analyze its material and figure out the exact final profile we need. Step 2, we identify our machining requirements, think production volume, required tolerances, stuff like that. Then we select the tool type, pick the material, determine that ideal cutting geometry we were just talking about, and actually calculate all the exact dimensions. Only after all that heavy math is done do we move on to creating engineering drawings, CAD modeling, physically manufacturing the tool, and finally putting it through rigorous inspection and testing.
Which brings us nicely to Section 4, Designing Non-Standard Tools.
When it comes to designing forming turning tools, engineers basically have to pick between two main architectures, prismatic and circular. Prismatic form tools are completely flat and actually need a special lifting mount to angle them correctly into the workpiece. Circular form tools, though, are pretty cool. They're built around a specific base radius, which means you can regrind them over and over again without ever losing that original, perfectly calculated profile.
Now, here's where it gets really fascinating.
because reality forces engineers to deal with some crazy geometric quirks. Check this out. When you use a flat tool face to cut a conical surface on a workpiece, the exact mathematical intersection of those two things isn't actually a straight line. It creates a hyperbolic curve. We call this inherent discrepancy the hyperbolic error, or delta 1. So engineers literally have to math their way out of it by calculating specific corrections right into their tool profiles to cancel the error out, making sure the final piece comes out perfectly straight.
And speaking of rigorous math, just consider the calculations required for a 4-milling cutter. To make sure this tool keeps its exact cutting profile even after being sharpened, say dozens of times, engineers have to calculate what's called a specialized back cut, or relief curve, right behind the cutting edge. This isn't just simple addition. We're talking about calculating logarithmic or Archimedean spirals so that the clearance angle stays perfectly constant even as the tool's radius gets smaller over its lifetime.
So, what we're really seeing here is the ultimate design principle for non-standard tools. The required workpiece profile strictly dictates the tool profile. The math is essentially worked backward from the finished part. By plotting out coordinates starting right from the center axis of the workpiece, engineers translate those exact points to generate the required geometric envelope on the milling cutter or turning tool.
Okay, let's move on to Section 5, Designing Standard Cutting Tools.
You might look at a standard twist drill and think it's just a simple piece of twisted metal, but the engineering behind it is incredibly precise. Just think about the different variations we have. We've got low helix drills, high helix drills, and coolant feeding drills. That helix angle, the actual twist of the flute, is engineered very specifically for chip evacuation. A high helix is going to pull chips out of deep holes super fast, whereas a low helix gives you the structural rigidity you need for really tough materials. Even those tiny internal channels for the coolant, they are mathematically mapped out so they don't compromise the drill's structural core. Pretty amazing, right?
Now, when we need to bore much larger holes, engineers turn to spade drills. These use a replaceable cutting insert that gets mounted onto a really rigid body. Every single facet, angle, and dimension of that insert is mathematically defined. Because these inserts are meant to be swapped out, the engineering blueprint has to guarantee that the cutting geometry stays perfectly concentric to the tool holder, literally down to the micrometer, every single time you pop in a new blade.
Let's see how all of this actually comes together when manufacturing the drill itself. To carve out those deep spiral flutes on a twist drill, engineers use a form milling cutter in what's known as a non-center envelope method. Basically, they calculate a super specific profile for the milling cutter so that when it passes through the solid drill blank at a very specific angle, it leaves behind this perfect spiral flute geometry. And it leaves exactly the right amount of material right in the center for the drill's core web. It is an absolute masterpiece of precision.
All right, wrapping things up with Section 6, Designing Gear Cutting Tools.
If you want to understand the design of modern gears and the tools that cut them, you absolutely have to understand the involute curve. This is the foundational geometric principle at play here. Imagine taking a string that's wrapped around a cylinder and slowly unwinding it. The path that the very end of that string takes, that is an involute curve. Technically speaking, it's the locus of a point on a straight line rolling without slipping on a base circle. This very specific mathematical curve is the magic that ensures when two gears mesh together, they transmit power flawlessly without binding or slipping.
To manufacture that absolutely perfect involute shape, tool engineers have to design highly specific cutters for different kinematic methods. Take gear hobbing, for example. The tool looks almost like a threaded worm gear with cutting teeth, and it has to rotate perfectly in sync with the workpiece to generate the gear teeth using an envelope method. Then you have gear shaping, where the tool actually looks like a gear itself. It reciprocates up and down while slowly rotating along with the blank. Across all these methods, the one constant is that the tool geometry has to be perfectly, mathematically synchronized with the machine's movement to generate the final part.
It's honestly incredible to see how pure theoretical math translates so directly into the physical tools that literally build our entire industrial world. Every single angle, every curve, it's all a mathematically calculated solution to a real physical problem. But it definitely leaves us with a really fascinating question to ponder. As manufacturing precision continues to push further and further into the nanoscale, and we start dealing with wild advanced composites and exotic alloys, what completely new, previously impossible geometries are the mechanical engineers of tomorrow going to have to invent? The math is always evolving. Thank you so much for joining me on this explainer, and always keep questioning how the world around you is built.